Hey guys, today we're looking at day 2 for momentum, our second set of notes for momentum impulse, and in this case, today we're focusing specifically on collisions. So what happens when two objects with momentum interact with each other? We'll look at collisions and we'll also look at explosions. So, as we talked about yesterday, momentum is another conserved value. Conservation of momentum in one dimension is another thing that we're going to talk about here. Whenever we have two objects that collide, so when they exert forces on each other without colliding, such as gravity, that's another scenario that we're looking at here. Momentum of the system, so the interaction, the whole, whatever the scenario is, all of the combined forces and situations and objects and everything, the momentum of that total system is conserved. Meaning, if we're looking at momentum of two objects, as they approach each other, after they interact, and then after they leave, the total momentum is constant throughout the whole thing. So we might have objects that change momentums, but the sum of the momentum before and after are going to be equal to each other for the collision. So we look at this. We've got an equation here for a total momentum if we have objects interacting with each other, and this could be different based on if we have more than one object before, maybe they're starting together and then they explode and they separate out into different objects. But in general, when we got two objects interacting with each other here, we've got mass 1 and volume 1, mass 1 and velocity 1, mass 2 and velocity 2. They're going in different directions. So it doesn't really matter which one you call which one you say is the positive direction and which one you say is the negative direction. But as we set up our p-value, so our momentum of the whole thing before, we've got mass times velocity for object 1, mass times velocity for object 2. But here what we're considering is positive moving to the right, and that means that negative is going to be moving to the left, which is why this is a subtraction here in the middle, because this velocity is going to the right. This velocity is a leftward one, so that means this has to be a negative velocity, therefore a negative momentum. And again, it doesn't matter which one you call which. You're just going to designate a direction and then make sure that those match. So if they're going the same direction, they could both be positive. If they're going in opposite directions, one has to be positive, one has to be negative. So after they interact with each other, we've got that same mass 1 and that same mass 2. Those are not going to change in this case because they're just interacting with each other, colliding, and then going in opposite directions. We are going to have new velocities. It's not necessarily they're not going to exchange velocities. They could be totally different, and in most cases, actually, they are totally different numbers. So we'll just call this v sub a for velocity a, and then v sub b for velocity b for the individual objects afterwards. Notice here, because of how this picture is drawn, my masses collided with each other and they both went back in opposite directions. So notice here my signs changed. Now mass 1 has a negative momentum and mass 2 has a positive momentum because afterwards mass 2 is moving to the right and mass 1 is moving to the left. So we had a little bit of a change there. Now again, because we know the total momentum is conserved, these two things, my momentum before and my momentum afterwards, have to be equal to each other. So that's going to be the equation right here that we're going to be utilizing for most of these problems, if not all of these problems. There's going to be some adjustments that we'll have to make to this, and we'll take a look at that a little bit later and also on our collisions worksheet that we'll be working on tomorrow. But again, you've got before on one side, after on the other side. You find that total momentum beforehand, you find the total momentum afterwards, and you'll be able to figure out that those are equal to each other, or in most cases, you'll be able to figure out what the momentum was before, you've got some aspects of it afterwards, and you'll be able to figure out the rest. So let's get into a little bit further. We could have an example here where, what am I saying here? In the last slide, we were drawing the opposite directions. Oh yeah, this isn't always the case. So if you ended up with something where you predicted it to be, going in opposite directions, if you ended up with a velocity, let's see, say you, in this situation, just as drawn, you would predict that after they interact with each other, mass 1 now has a negative velocity and mass 2 has a positive velocity because it's going to the right. If you end up with something where you set it up and you assume that that's the case, but you end up with a negative velocity for, let's say, v sub b, you have a negative number, that means that after they interact with each other, they collide with each other, now they're both moving to the left. So it could be something where that happens. It doesn't necessarily mean that you're wrong with the numbers that you got. It just means that the direction that we thought would happen didn't happen. And that's okay. You just drew the vectors in the wrong direction. They end up interacting with each other, and then they both slide off in that same direction. All right, now let's get into an example problem. So totally realistic. Maybe it is around here. Who knows? People are bored, especially nowadays. So for example problem number 1, we have a rifle. Someone fires a rifle, I guess fires a bullet from a rifle into a giant slab of butter on a frictionless surface. So again, here we're pretending, I chose butter because it's, we know it's super, oily and it's super slick if you have it on the right surface. So we shot a bullet at a big block of butter, and it has, it's on a frictionless surface. So I mean, it's going to slide easily. There's no other outside forces acting on the two objects other than the butter and the bullet. So they're going to interact with each other, and we'll figure some stuff out afterwards. The bullet penetrates the butter, but while passing through it, the bullet pushes the butter to the left, and the butter pushes the bullet just as hard to the right, slowing the bullet down. If the butter skids off at 4 centimeters per second after the bullet passes through it, what is the final speed of the bullet? In this case, the mass of the rifle does not matter. Matters not. I guess I talked like Yoda in this case when I made this. So this is beforehand. The information that we're given, 35 grams is the mass of our bullet. It's traveling at 700 meters per second. Our block of butter has a mass of 7 kilograms, and since it's sitting still, we know it has a velocity of 0. And then afterwards, after the bullet has passed through the butter, we know that the masses have not changed. We're assuming that there's no shrapnel or anything that's left in the butter, and the bullet's not pushing any butter off of the block. We're going to assume constant masses here. So my bullet is still 35 grams. My block of butter is still 7 kilograms. But now this block is sliding 4 centimeters to the left, and I'm trying to figure out what the velocity of my bullet is after it's gone through. So some things that we are going to kind of look at here. We always start off by choosing a direction to be positive. In this case, since everything is moving to the left, I'm just going to call that positive. So everything is going to be positive to the left. It doesn't matter which one you call which. I think it's just easier to keep everything positive when we have the choice to. In this case, everything's definitely going to be positive moving to the left. And then we're going to use our conservation of momentum, convert all units into meters and kilograms. So some things we have to be careful of. Again, our given information that we started with. Our bullet the mass was given in grams. We know that our standard units for mass are kilograms. The other thing we have to make sure matches, we've got 700 meters per second is our initial velocity of the bullet, but only 4 meters per second, 4 centimeters per second is the velocity of the butter afterwards. So I have to make sure that those match, and that my mass for my measurements for the mass, my units for the mass match. And it's usually easier just to convert it into our standard units. So we're going to go ahead and start doing that. Our converting from 35 grams to kilograms, we know a gram to a kilogram is just moving the decimal place 3 spots to the left. So our momentum beforehand, right, 35 grams, 700 meters per second. So the momentum of the bullet is given here, 0.035 times 700. And in this case, actually, since our butter is not moving, it has no momentum initially. So, right, it still has a mass of 7 kilograms, a velocity of 0 meters per second. So I can just add those together, which really is just the 700 times 0.035. So before the bullet and the butter intersect each other, or interact with each other, collide with each other, they have a total momentum of 24.5 kilograms times meters per second. And we know if that's the momentum before they interact with each other, that momentum has to be the same afterwards. So Afterwards, after they've interacted with each other, the butter is now moving at 4 centimeters per second, which is, centi means 100, so that's 2 decimal places to shift it over. So this is moving actually at 0.04 meters per second. Again, we know my mass of my bullet is 0.035 kilograms. So this is the part where I'm trying to figure this out. I know afterwards my butter has a mass of 7 kilograms and has a velocity of 0.04 meters per second. So that part is 0.28. I know that my mass hasn't changed for my bullet, and I'm trying to figure out that end velocity. So I'm going to be solving for this v. So I know that before is equal to after, so then this 24.5 that was my momentum beforehand has to equal this that I just set up. So 0.28 plus 0.035 v. So I'd subtract, just like if I was solving a problem back in Algebra 1, I would subtract 0.28 from both sides first and then divide by 0.35 to get a velocity of 692 meters per second. So not a whole big change, because if you look at it, my velocity only decreased by 8 meters per second, but it's a big block of butter that we're firing into. So in this case, my V did end up coming out positive, which means the picture that we drew of the direction of the bullet afterwards is correct, right? Which makes sense. I mean, we would be very, very startled and surprised if we shot a block of butter with a bullet and the bullet didn't continue going on its path. It would not rebound off of it and come back the direction. So that would be one way of using it, one way of utilizing conservation of momentum. Example number 2 is a little bit different. So example number 2, so we've got these things called, and I don't remember if I addressed this or not. It doesn't look like I did. I don't think I did. We'll talk about it before the worksheet tomorrow. We have these 2 different kinds of collisions. We've got something called an elastic collision and an inelastic collision. And really the big difference is whether the objects before, so we know before and afterwards, right? They're always going to be starting as single objects, right? 2 separate objects. In an elastic collision, or if you think elastic like stretchy, bouncy, they're going to interact off of each other and they're going to leave as still 2 separate objects. In an inelastic collision, which is what we're going to be dealing with here for number 2, the 2 objects collide and they stick together. So they're stuck as one object. It could be one lodged in the other, like we have here with the wood block instead of a butter block. It could be something where they just attach to each other, maybe 2 cars get in an accident and the metal gets all mangled and they start getting intertwined and they just get stuck together. Sometimes that happens. But that's the difference between an elastic collision and an inelastic collision. But I'll do a little bit more on that tomorrow when we're working on the collisions, because that does make a big difference. Because here, the same problem, but now the block is made of wood rather than butter. The bullet doesn't pass all the way through it, but all the same variables. Still 35 grams for the bullet, 700 meters per second, 7 kilograms for the mass of the block, and that's sitting still. So we know beforehand it had a mass of 0.35 times 700. Right, that was the 24.5 was my initial momentum. Afterwards, now it's just a single object. So it's not like M1V1 plus M2V2 equals M1VA plus M2VB. In this case, it's see if I can, let's do a pen here. We end up with M1V1 plus M2V2 equals M1 plus M2V. Apologize for my sloppy handwriting. I had not planned on writing anything down. But that's, again, they're together. It's a one combined mass that we just add them together. Their combined mass times the end velocity of that single object moving forward afterwards. So this M1V1, M2V2, we have, really we could have said, 7 times 0 to get the M1V1 for the block. But really we know that the total momentum beforehand is just the bullet, right? 0.035 times 700. That has to equal their combined mass. So you're literally just adding together the 7 kilograms from the block of wood, the 0.035 kilograms from the bullet. So that mass is 7.035. So we end up with a total velocity together afterwards of 3.48 meters per second. So much slower. Here, once again, we notice that it is assuming a frictionless surface. Otherwise, there would be a frictional force on the wood in addition to that of the bullet, and the system will have to include the table as well. So like if it was sitting on something here, we would have to include that as part of the system. The momentum beforehand of it would have to be included in that for the mass. If it had friction, but here again, we're assuming a frictionless surface. Maybe it's on an air hockey table or something like that. But that's how we would go through and find that that momentum afterwards, the velocity afterwards. All right, last problem number 3. We've got, I was obviously very loopy when I was making this the first time, and I just decided that I want to keep it there because the randomness of my brain and why I have crates full of raspberry donut filling and a tub of lime Kool-Aid colliding with each other, but that's just what I visualized when I was doing this. So we're going to go with it. We've got a crate of raspberry donut filling that collides with a tub of lime Kool-Aid on a frictionless surface. Which way on how fast, it's supposed to say which way and how fast does the Kool-Aid rebound? Let's draw V in the right in the after picture. So here is before. This is our information that we're given beforehand. Our raspberry donut filling has a mass of 3 kilograms and is traveling 10 meters per second to the right. Our lime Kool-Aid is a mass of 15 kilograms moving to the left at 6 meters per second. So as they go through, they're going to hit each other, collide, and go back in the opposite direction. We know that afterwards, the raspberry donut filling has a velocity now of 4.5 meters per second to the left. We're trying to figure out how fast and in which direction my lime Kool-Aid rebounds. So what I have to decide is how to start, right? So here I said, let's draw V to the right in the after picture. So we're just assuming here that they interact with each other, they collide, and they're going to go in opposite directions. So I'm going to call right positive and left negative since I've got both of them. Here I would go through, I obviously didn't animate these individually. Beforehand, 3 times 10, and then negative 6 times 15 is the total momentum beforehand. And then afterwards, my negative 4.5 times 3, since this is moving to the left, and we're assuming 15V is moving to the right, just assuming that. As you go through and solve this, this is 30 minus, what is that? It's 90, so negative 60 equals that. So we'd have to, again, we're going to do a little bit of math here. But as you go through and do this, I'm not going to bore you guys with being able to do that because I know all of you are more than capable of doing simple math problems like this. We end up with a V of negative 3.1 meters per second, which tells me that since it's a negative, my arrow is actually drawn in the wrong direction. This one has so much mass to it compared to the other one that the raspberry donut filling and the lime Kool-Aid are going to come towards each other, collide, and actually it has so much more mass, the lime Kool-Aid, that it's going to continue moving in that same direction. So it's got an end velocity of 3.1 meters per second to the left. So that's all I got for you guys today. That is the last slide. As always, if you guys have questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting me know. Tomorrow, you will be working on the collisions worksheet. You guys already do have a physical copy of that if you wanted to start working on it, and I'll be posting the Kami worksheet version for those who like using the computer for it. But again, that'll be what we're working on tomorrow, and then we'll get into kind of reviewing for momentum, collisions, impulse stuff to be ready for our momentum quiz on Friday. So have a fantastic day, and we'll see you guys soon.